Okay, so the last day. Woohoo! We're going to do EFA and a little bit of PCA. Mostly just to talk about why you shouldn't do PCA. So this is the last topic. It's very different from everything we've been doing because this is not hypothesis testing anymore. This is exploratory data, hence the explore part. / descriptive analyses is often what this gets lumped in with. This is sort of the precursor to a structural equation type of model where you have lots of IVs and DVs. If you're interested in SIM, Mitchell will talk about it next semester, and then I always teach it over the summer. It's also part of the STAT certificate that we offer that will be official as long as Faculty Senate passes it this week. So you can actually apply for the certificate starting next fall. Woo. Yes, that has been a lot of work, so yay me. If you have questions about it, I am the coordinator. You can send them to me. So, but today, EFA. So there's going to be a lot of new terms and a lot of squiggles on the board, but it'll be okay. So everything we've done this semester has been a measured variable. So measured variables are things that you get from an experiment. So they're the real scores a participant gives you. So anytime people draw these sorts of things in like a structural style, they're a square. So you might have question 1 on the exam, question 2, question 3, let's just do 4. So they're denoted by squares. So if you ever see a paper with a structural equation model in it, if it's a square, it's something they actually measured. They got that from a participant somehow. Latent variables, or unmeasured variables, are the things that the squares are supposed to represent. So if I have a scale, the scale today is my R anxiety questionnaire, it's from the book. It's supposed to measure anxiety. Clearly, it's got anxiety in the title, right? But it also might measure math. So the latent variables are the things we're trying to get at using these scales. So I think a little bit everybody's been doing IQ testing. So the scale itself is the WAIS, or WISC, or WIPSI, or whatever other alphabet soup, Tony. But what you're trying to get at is IQ. So you're not actually measuring IQ, you're measuring things that are supposed to measure IQ. So those aren't measured directly, and they tend to be drawn with circles. Okay. So squares are real, circles are not. So we can say working memory and visual search or something. So we have things that we're measuring to try to represent, give us an overall picture of these latent variables. So the point of EFA and a lot of structural equation modeling is to get at these latent variables. So I'm going to use these measured variables to represent the latent variables and then do something else with them. So I found this one online, just searched SIM diagram, this is what came up. So they have their questions for brand advocacy out here. So all of these squares were measured. Clearly they've got the little question label on them too, so that makes it really clear. Right. And then these circles here are what those questions represent. So they have 3 questions that represent commitment to brand, 3 for product performance, right? And I've got 2 over here for brand advocacy. And they're using these circles to predict brand advocacy overall. Okay. So the direction of the arrows is important, and that's where we're about to get to. So if you see these sorts of diagrams, what they're doing is taking measured variables and using them to interpret overall constructs. Ooh, fancy slide, whoa. So this will get into the difference between EFA and PCA. Okay. So factor analysis is what we're going to do, like typing it up. It's not hard to switch in R to PCA if you're interested in doing PCA, but theoretically most people in our field don't recommend PCA. So what factor analysis does is it takes these questions, and we're trying to explain the maximum amount of common variance. So I try to bold or italicize the words that are important in this section. Okay. In a correlation matrix, so we've got a correlation of all those questions. And what we're going to try to do is take that correlation table and smush it together. So we're going to create these factors by taking those correlations that are high and making them all one thing. So it's also a way to take multicollinearity and make it one construct instead of 5 or 6 questions. So factor analysis creates factors by exploring the common variance. Common variance is overlapping variance, so this is R squared. So we're trying to interpret R squared for different questions, items. PCA, so principal component analysis, tries to explain total variance. So it's trying to explain R squared and the error in a correlation matrix. And that is the biggest distinction between the two. There's two big distinctions between them. Hint, this is usually an in-class question. One of them is that the EFA is about common variance, PCA is about total variance. Don't tell me it's factors and components. That's really obvious from their name. But PCA tries to explain all of the variance, and it takes the original variables and makes them components. Mathematically, in the background, this is still regression. This is regression on steroids. STEM is regression on coke, because you never know what's going to go wrong. So EFA is still regression. That's why it's in this section. So we've got factors and we've got components. And don't interchange the two. So this is a really great paper called Exploring Tom Swift's Factor Analysis Machine that lots of people use to say these are the rules for factor analysis, is where most of this lecture comes from. So don't say components when you mean factors. So stick with the term that matches the analysis, or people will think you don't know what you're talking about. So common variance is our systematic variance. So it's the overlapping variance between items. So if you give people a scale, you don't want like random questions. You want them to overlap because you're trying to measure this construct, this latent variable, by asking several different questions. So you're trying to like take the variable, it's our latent, and say, well, okay, this one's question 1, this one's question 2, this is question 3. So they're going to overlap because they all measure the same underlying latent. But you want them to measure different pieces of the latent. If you have questions that don't relate to them at all, they're going to be out here. I have this picture on another slide here in a second. So common variance is the overlapping variance, and we tend to think about this as systematic variance because that's the point of one of these analyses, is to figure out what variance overlaps. Unique variance is error, so it's all the things that don't correlate with anything. So the non-overlapping piece or this whole variable. So to kind of sum up this slide, here's the simpler form. EFA is common variance only. PCA is both. And you'll see this, the estimates of these in the output. Common variance is listed as H2. I forget why. It's an H. I know, that's not mnemonic at all. Unique variance is U. That's a little easier. So communality or common variance is going to be H in the output. Unique variance is going to be U. And they will add up to 1 because we're partitioning the proportions of variance. So it'll total up to 100%. And really the only reason I explain PCA is so that you can understand the difference between them. So when people say, well, why didn't you do PCA? You'll be like, because no, bad, stop. All right, so communality, or the H1, is the common variance for each item. So you can think of it as a squared multiple correlations. Some programs list them as SMC. R does not. It lists it as H. But essentially it is R squared for each item. So instead of having R squared for one DV, we have R squared for each item. And we want those to be really high. And the way it's created is using that, taking this item and making it the DV and using all the other ones to predict it. So if I can predict all the variance in question 2 based on all these other questions, it's a good question. So I want these to overlap. Multicollinearity is now good. Because that hasn't been confusing all year, I'm sure. Okay. So usually it's bad. Repeated measures, it's going to happen. Just give up now. Now it's a good thing. Here's the picture. I didn't realize it was going to fly in sideways, but okay. So communality is the overlap. So for variable 3, it's got a communality of 1 because it overlaps completely with these other variables. Okay. Variable 4 has a communality of 0 because it overlaps none with the other variables. So I can predict all the variance in variable 3 with questions 2 and 1, and none of the variance in variable 4. Okay, so we want this. You don't want this. So most of the procedure in EFA is reading these questions out and getting rid of them. So the reverse is also true. So uniqueness for variable 3 would be 0, and uniqueness for variable 4 would be 1, because it adds up to 1. So the way people used to have to do this by hand, which was miserable, I'm sure, was look at a correlation matrix and see where the correlations overlapped a lot, and then did some evil math to combine them into one score. Okay, so I have these high correlations here. Those questions would go together. These questions would go together, and they wouldn't overlap. So this is nice and low here. So we're trying to find a way to say these 3 questions are one thing, these 3 questions are another thing, and they don't overlap that much. But that sucks. So let's do this a little bit easier way. I'll make the program do it. Here's the other big distinction. So common variance, unique variance. The other distinction between EFA and PCA is the direction of the arrows. So in EFA, the factor, or the latent variable, is thought to cause the questions. This is what gets most people. Okay. So I'm going to take these things that I measured and come up with an IV that I didn't measure to predict them. I know. It's okay. So what happens is we're trying to figure out what these variables are, given that we know the correlations here, but we assume that the reason people answered the way they did on the scale is because of that variable. It's kind of a theoretical idea that if you think about IQ scales, you know that IQ causes their answers. Yes, I measure their answers and I give them a score, but we don't think that I gave you a score because of these answers. It's your IQ caused you to answer this, which is this score. So EFA, we think the latent variables cause the answers, the output. Most people don't totally talk about it that way because you can't really do cause and effect, because really this isn't measured. But it's this thought that like this underlying thing in you causes the output that we see. Okay. And that's generally when we're trying to generalize to another sample. We want to use this scale to measure across multiple things. This is probably 60% of my publications are on scale development. And so generally this is used to validate a scale and say this scale will then predict these other things. Now let's use that scale in a different sample and make sure it still works, and then repeat. Recently got to do one with the Swiss Spinal Cord Institute, looking at a scale that we had developed and how it worked in a pair of people with spinal cord injuries. So cool. And we got this huge argument about EFA and PCA. I was like, listen, psychology, no PCA. Don't do it. And PCA questions are reversed. Okay. Question 4. We think that the questions cause the latents. So the arrows go the other way. That's generally for description of the sample. PCA, that's really unusual. Okay. And this would be more if you were manipulating the questions. Excuse me, too much garlic for lunch. Or the thing I think about for PCA is if you have like a demographic set you're trying to use, I don't think your demographics caused your SDS. That doesn't really make sense. So I'm going to use SES and some other things to create a demographics overall. And that makes more sense for the arrows to come in. Right, so it might be my demographics of the sample, and I'm going to use socioeconomic status and gender, because I don't think your demographics cause gender. That's about the best example I've got for PCA in psych. I know they use it a lot when they do some EEG stuff, but they're not doing scale development usually. So EFA is more common in psych. Because the way we talk about theory is that this construct causes these answers, so it matches EFA. People will interchange them as if they are the same math. They are not. So if you ever have somebody be like, wow, PCA does the same thing, you can be like, no, notes. I can give you the real citation for it. All right. So the two big things, common variance versus common and unique, and then the direction of causality are the differences between them. So why would I use either one of them, though? Especially EFA. And generally it's scale development. So I'm trying to understand the underlying structure of a set of variables. It could be items on a questionnaire, like question 1, 2, 3. It could be a bunch of different variables. So I've used an assignment before where we had people look at the different subscales of the weights. They're so correlated, it's a pain, but understanding how those subscales go together. So it doesn't always have to be one single question. It could be a subscale score of a bunch of different items. One of my first publications was looking at these for different types of semantic and association variables. So we were using different mathematical ways to calculate things to look at how they group together. So it isn't always scale development, but most of it is. So that's the track we're going to take. I also could use it to take a data set that is huge and reduce it down to smaller forms. Sometimes you'll see that called what does the S stand for? Vector dimensionality. It's called SVD. Just jumped right out of my head. Single vector decomposition. Something like that. Where I take a huge data set, I have 400 variables, and I'm cramming it down into smaller variables. But we're going to focus on the scale development half. And then if you're really interested in scale development, we have a tests and measures course that talks more like how to develop the items. This is the stat end, how to test those items. Okay. So from the example from the book, those two factors don't seem to overlap that much. So we have this factor of items, this factor of items, so these three go together because they correlate together, and then these three go together. We're going to talk about rotation here in a minute. Graph. The cool thing about this is you guys will be happy there are no graphs. Yay. There are tables instead. So what we're going to do is take this statistics anxiety questionnaire from the book, and I included the Word doc online so you can look at the questions. So they're really funny. Statistics makes me cry. My friends will think I'm stupid for not being able to cope with R. The one reverse-coded item, standard deviations excite me. Pearson attacks. So they're just like goofy questions about statistics and R and computers and math. So lots of these questions overlap, but it's not perfect because are we talking about statistics? Are we talking about computer anxiety? Is there some math questions? So there might be 2 or 3 factors on this thing. Okay. I weep openly at Central Tennessee. I find it funny, but I've also read both versions of the field book now, so like we have the same sense of humor. But he's clearly British too, because I don't know how much duveying that we do here in the States. But we're going to take that scale and try to run an EFA on it, and we're going to do this in steps. So this sort of 3 sets of question things is something I made up for a book chapter that I wrote that just hopefully will help you see, like, here's how I do one of these. And like I said, most of this is taken from a couple of different books and the Preacher article. Okay. So the first thing you have to do is make sure you reverse code anything that is not already reverse coded, or it will throw fits at you. Okay. If you ever want to hear the best rant about reverse coding ever, go find Dr. Vizio and ask her about reverse coded items. And be prepared for about an hour of your life. So people say you should reverse code items or reverse word items so that you can tell if people are faking, and it's just better to have some positive and some negative. I will tell you that the reverse coded items are the worst. They're so difficult to deal with. They're often the ones that get tossed first, because there's something about when people are answering questionnaires that they tend to give like different answers, which is an interesting statistical question too. All right, so the 3 libraries we're going to use today. Car, you should already have. Psych, I think we installed the other day for something. But GPA rotation, you probably don't have. So you'll want to install that. Okay. The assumptions are the same. So we got accuracy and missing. Now for missing data, often you'll be able to fill people in, because you'll have enough questions that 5% will be a good rule. Outliers, just Mahalanobis. So yes, I know this is regression, but it's not the same type of regression, so back to just Mahalanobis. It really has to be linear, or this won't work, because it's lots of regressions at once. Normal, homogeneous, and homoscedastic. So no multicollinearity, because that is the point. Now, if it doesn't run, you might check multicollinearity to make sure that they aren't perfectly correlated. It won't like that very much. But if they're correlated pretty highly, they're going to get grouped together. So it might be a check when something doesn't work, but otherwise, you know, like I want them to be correlated. Yay! Let me get the data set loaded here. So we've got tons of people. We're going to talk about how many people you need in just a second. What, 2,500 people, because it's made up data, and a ton of different questions. So it's 23. And let me load my libraries here. Yeah, that's nice. So the first thing you want to do before we get into other stuff you have to run is make sure you reverse code the items. Okay. You will have to do them one at a time, as far as I can tell. Unless you have the whole data set needs to be reverse coded, I don't know. So it's a new function called recode. You can't use relevel because you don't want these to be factors. I'm not sorry, relevel. You can't use factor because you don't want these to be factors. Okay. I guess you could factor it and unfactor it, but this code works pretty well. So the recode function is recode the name of the column. So I'm pretty sure it has to be one column at a time. So question 3 is our reverse coded item. And then all of this has to be in quotes. Okay. There's no C, just quotes. Okay. So 1 equals 5, 2 equals 4. So I'm just telling it to reverse them. You don't have to do 3 equals 3. It will figure that out, but I just went ahead and did it to make it obvious what I was doing. Okay. You can use recode in a bunch of different ways, and they have more examples if you search the help. But this is very basic reverse coding. Okay. So I could do 1 equals 5, 2 equals 5 if I wanted to collapse 2 of the categories together. All right, so let's look at it before. So my table before says I have 76 ones. If I run line 20 and look at the table again, now you see the tables have just flipped. So that table code isn't necessary, but if you want to make sure that you're doing it right and that they've just flipped around, that'll help you see it. Right, so always start by reverse coding your items. Okay. But what about additivity? Okay, so I want these items to be correlated, but not too high. Otherwise, the math gets screwy. But don't worry, it'll tell you. It'll usually give you a matrix not definite error. Okay. But the other problem is you don't want them to be too small, or you're wasting your time. Okay. So if none of the items are correlated, this EFA thing isn't going to work, because that's the point. So take them correlated. So there's Bartlett's test, and you want it to be significant. Okay. So if it's non-significant, that implies your items are not correlated enough, which would be bad. Okay. It is not used very often because EFA requires large sample sizes, and large sample sizes make this significant. So it's a little bit of spinning your wheels, but I've seen it more often than not lately. So I think it's making its way back around to being popular, so I just wanted to make sure you knew how to do it. But the one problem with it was very large samples. It'll come out significant either way because of power. Right? So power is bad in this situation. However, if you have a small sample and it doesn't work, your EFA might still run because same issue of power on the other side. But here's how we do it. Right. So you want to load the psych library. Everything for EFA is in psych. There is factor analysis in base R, but it does not do a lot of the things that you want it to do. And it has a terribly unfortunate name. It's factor analysis, right? So they did it as fact anal. Every time I was like, I can't handle this. So psych also does the other stuff we want to do. So we're just not going to use base R. Okay. All right. So the first thing you have to do is run and save the correlation test, just like you would have done for data screening, and then run symbols for numbers on it. And then core test.bartlett. So go back over here. So first thing you have to do is run a correlation table. As part of the test, there's going to be you're going to have data that has like questions for an EFA and then questions for a regression. And what you want to do when you do the EFA is just pick the questions you want, make it like EFA data set. Does that make sense? So drop all those other columns. And the reason you want to do that is because it'll be much easier if you aren't always like exclude these last four or something. So just kind of make yourself like, here's my EFA data set. So correlations on EFA data. Has core.bartlett, so it's correlations, and you have to tell it n, or it assumes n is 200, which is just silly. Okay. And to make that where I didn't have to remember every single time, I did n row. Remember, n row will tell me how many rows there are. So let's look at what that gives me. So it's a chi-square test that the correlations are big enough. I don't know what that means really, but it gives me my chi-square value, p, for my degrees of freedom, and it's significant. So you just really want to look at p-value here and say, yes, it's significant. But if you wanted to report it, I don't think we've reported any chi-squares this year. No, I am. It's chi-square. Degrees of freedom, degrees of freedom. Oop, that's a 9, not a p. I gave you p equals 0 because that p-value is so large. Large meaning very, very small. Okay. So I do chi-square degrees of freedom, the actual chi-square value here. And then this is p dot value. All right, so Bartlett's test is significant. So I would say that my correlations are large enough. They should be correlated enough to do something with. So that's kind of where additivity comes in. Oh, we did that. Okay, let me get through the before you starts, and then we'll take a break. What about sample size? So the suggestion is 10 to 15 per item. I've seen that in a lot of places, mostly 10. So if I have 23 items, I need 230 people. Less than 100 is not acceptable. They will not publish it. Please ask me how I know. We had 98. It got published in a different form, but EFA wasn't acceptable. So it's like, whatever. Okay. I feel like that is slowly going away with Bayes and bootstrapping, but still, like, people just don't think that's enough people. So there are lots of arguments. I've seen lots of talks on this. So many Monte Carlos. Remember, Monte Carlos are different ways to test statistics, and most people agree that 300 is your best bet. So shooting for somewhere between 100 and 300. 300 is like the golden rule. If you have 200, most people won't blink. The closer you get to 100, the more cranky people are. So that's how many people. We've got 2,700 in this data set, so we're okay. But there is a way to test that, and this is pretty popular. So it's the Kaiser-Meyer-Olkin, or the KMO, sampling adequacy test. Do I have enough people to adequately fit a structure to an EFA? So it compares a ratio between overall common variance and sort of a unique type of variance, so R to PR, and you want common variance to be much larger than unique variance. So scores closer to 1 are better, closer to 0 are bad. And then these are from the book. Those are not his terms, clearly, but these are kind of the criterion, right? If you're over 0.9, it's really good. 0.8 is okay. 0.7, eh. Below 0.6, people think you don't have enough people. All right. So how do I run that? Still in psych, and it's that saved correlation table we already used. It's really easy. It's KMO and then the saved correlation table name. Let's run that. Let me blow this up so I can talk about what does this mean. So the overall MSA. Oh, dang. I looked up what MSA meant the other day. Measure of sampling adequacy. Yeah. Cool. I can remember things. Okay, I can't remember to upload the notes, but I can remember random abbreviations. So overall measure of sampling adequacy, or what the KMO test came out to be, is 0.93. So this is really good because it's made up data. So this would be in the yay category. But then it also shows you for each individual item what their ratio would be. And so you can almost kind of tell at the beginning which items are going to be bad. So if you have a bunch of items that are 0.9, 0.9, 0.9, and then like 3 that are 0.2, that's going to be bad. So it's kind of like a precursor to the next couple of steps. But overall, you want to be 0.9. So, oh, I was on the notes. Here we go. So that will allow me to tell if I have an adequate enough sample to do a factor analysis. Right, and then the last one is how many items. So if I'm creating these latent constructs, I don't want to only use 2 variables. Okay, so most people agree that 2 items is not enough to measure a construct. You need at least 3, preferably 4. So what will happen sometimes, I have an example of this, is you'll be whittling out the bad questions, and then one of your factors will only have 2 questions at the end. Almost like that's no good. So you would get rid of the factor. So if you have a 10-question scale, you can probably only have 2 or 3 factors come out of that scale, if you have at least 3 or 4 of them. And so this is the only time you'll hear me say this, but the more people, the better. That's true all the time, but the more variables, the better. Because you can always get rid of the bad variables. And this is like the only time. Normally it's like, keep it simple, stupid, right? Not so many variables. But EFA is like, go, let's do all the variables. Right? Which is why we have a project right now that I think has 1,000 columns in it. You put all of them together. Not doing an EFA on that, but we could, I suppose. It would take forever. Okay, and the scale has to have at least interval measurement, but that's been true of everything we've done all year. Okay. So you cannot use, okay, I lied. You can do categorical variables, but you're better off doing an item response theory analysis on that. Okay. So generally EFA is for continuous data. IRT is also a different theoretical approach. You can also do it on continuous data. But if you have yes-no variables or the Likert scale kind of things and you want to analyze it that way, IRT is better bet. Okay. All right, so let's take a break there because then we'll get into what I do next.